we will find that they're not equal all the way down now. The top at a given point will always be higher than the bottom. So what good is this? Well, this is the one system where we can get to the bottom of this whole pretending that positive charge flows. Let me draw the system, what's really happening. So if we hook up a battery like this to a conducting plate, it is not really positive charges flowing to lower voltage. We've known that. But we've said, what harm is there in pretending? Now let's look at the real deal. We know that it's actually electrons heading towards higher voltage, right? That's what's really happening. So, of course, if there's no magnetic field applied, those electrons are just going to shoot down the middle of the plate. So let's try to apply the exact same field. Again, the magnetic field is going to point into the page. And let's see what difference that makes, if any. So, same deal. We have an electron moving left. I want to slap that into the magnetic field. So we get B slapped into B, forces down, but remember it's a negative, so it's actually up. So this is going to curve up, and electrons are going to drag across the top. So you will find electrons dragging across the top. Of course, that means that there are positively charged nuclei on the bottom that are not paired up. And how many of those participate in that dragging across the side? Well, enough so that the other ones don't want to, right? But here's the interesting part. If I were to compare the voltage here versus here, which one is the higher voltage? The bottom. So now there is again a lateral voltage difference, but the bottom is the higher voltage. We finally figured out some kind of phenomenon where it seems to matter what is it really happening. Is it positive charges going towards lower voltage? Is it negative charges going to higher voltage? Okay? So once someone thinks up this thing, a guy named Hall, okay, take it to the lab. There's going to be one answer. So if you actually go and do this in a lab, which do you think you will measure? Do you think that the bottom will be the higher voltage or the top will be the higher voltage? It's the bottom. This is the actual physical reality. This is how they figured out what is actually flowing. And I'm sure about 5 seconds after this, Hall was, wishing Ben Franklin hadn't chosen his convention the way it was chosen, right? So this is the one phenomenon we've looked at so far where it matters that you pretend, the pretending that the charge carriers are positive and it goes to a lower voltage. This is the one thing where you get the wrong answer, okay? Every other thing in this class, it doesn't matter. So pretend positive charge goes to lower voltage. But this is the one scenario we can concoct where there is a difference between positive charge going to lower voltage and negative charge really going to higher voltage. Of course, if you get in the lab and you measure it, what do you find? Well, really, it is electrons going to higher voltage. Okay? So this is how they figured out what is the sign of the charge carrier in motion in a circuit. What is the actual thing doing the moving?
Why didn't they just switch it?
Switch what?
The conventions. Like, why not just change at that point? Like, once you know?
Well, that's like asking why do we still use 120 volts in our electrical sockets whenever the whole entire world uses 240. Because we already have everything in place, and we're lazy, and we don't want to go and overhaul everything from the beginning. It's easier just to contend with the annoyance of it. Frankly, I mean, it's just historical holdover. There's lots of things like that. Yeah.
So in a situation like this, you have the lateral voltage drop, but then you also have
The main voltage drop. That's right.
So the voltage in like the upper right-hand corner. Yeah, I mean it's.
Yeah, like if you wanted to sketch it, like we
everywhere.
can make a graph of the voltage going across this thing, like going from left to right. if we did it going across the bottom, that's the higher voltage, so it might drop like this, right? And then if we did it across the this one, which is always at a slightly lower voltage, it'd go like this, right? It'd be just a little below at all times. So as we move from left to right, the voltage drops. But if we compare this would be, which one? This would be the bottom, and this would be the top. We're going to find at any given location, the bottom always beats the top, right? Does that sort of make sense? So this is the major voltage drop, but there's a slight voltage drop at any given location between the two sides. Okay, any other questions on that? Okay, so that's just a little bit of an aside and hopefully doing the velocity selector together with the Hall effect really helps you understand they're more or less the same deal, with the exception that in the Hall system, these aren't separately provided charges that create a voltage difference. It's from the charges flowing themselves being knocked to one side or the other as they are flowing. Okay. So, any last questions before I go back to Faraday's law?
I'm sorry, you were just saying that the bottom has a higher voltage drop, but
The bottom has a higher voltage than the top, right? Because positive charges are higher voltage than negatives. Okay? So this is always, at any given point along here, if you compare the top and the bottom is a slightly higher voltage than the bottom. Did I do it backwards here? I did. Yeah, the bottom is, no, the bottom is the higher voltage, top is lower. That's right. Okay, so let's go back to Faraday's law. So Faraday's law is what is going to allow us to get an electric stuff out of magnetic stuff. On the left-hand side, you have an EMF that's every bit as real as the EMF from a battery. It can drive current, depending on the resistance. Okay, so this is Ohm's law right here. But there's going to be no battery in sight. The EMF is going to come from a purely magnetic phenomenon. So over here you have a magnetic phenomenon, this thing called magnetic flux. Our first order of business is what the heck is flux. If the magnetic flux changes with time, that's where your EMF comes from. That EMF will drive induced current, according to Ohm's law. And then we learned a tool for determining the direction of the induced current called Lenz's law. So that was that status quo law. And that's definitely by far the easiest way to figure out which way does the current flow. So we have to figure out what's flux. So magnetic flux, let's talk about that. Now, flux is a concept that I haven't talked about before because I haven't needed it, but anytime you have a field, whether it be electric, magnetic, gravitational, you can define flux. Before I even start to get to that abstract thing, I'm just going to define fish flux. Okay, so let's suppose instead I were a wildlife biologist, and I am exploring the health of an ecosystem, and I'm trying to figure out exactly what the health of the fish is in this river by counting them in some way. So let me say I have fish which are hypothetically swimming horizontally. So let's not let them swim vertically. You can't get too far in a shallow stream going vertically anyway. So how might you test the health of the fish? Well, of course, there's no such thing as counting all the fish. It's just not doable, right? You take a sample. So what you might do is you might put a ring into the water, and then you can count how many fish swim through the ring, right? And that will give you some idea. So things to point out is that if you can either get more fish flux, okay? So defining fish flux, I guess I can use the same variable. Feed is flux, fish flux, okay? So there are two things to consider. Obviously, you're going to get more things going through the ring. Oh, I guess I should define flux. Flux is basically counting the field through an area. So one of the things that will cause you to have a larger fish flux is that the fish population is just healthier, okay? So first of all is the higher density of fish but you also have to consider the size of your catcher. Because, of course, if you make your catcher really big, you make your ring really big, you might have more fish swimming through it, but that's not necessarily indicative of healthier fish. It's just that you're counting more of them because you just happen to have a bigger ring, right? Does that make sense? So you have to account for not only the number of fish that are going to swim through the ring have to do with the density of fish, and also how big is the thing that they're swimming through, right? The final thing I will point out is that if your catcher is set up like this, it doesn't matter how many fish are in the river, it does not matter how big the area is, no fish are going to swim through it, right? It's oriented incorrectly. Fish are going to swim just above it or just below it, but if your counting mechanism requires that the fish swim right through it, no fish are going to do that. So there is also an orientation factor. The orientation of your catcher matters too. So that could kill the whole thing. So the orientation of the catcher notwithstanding, if we have a higher density of fish, that will cause a higher flux. If we have a larger area of the catcher, that will also create a larger flux, assuming that the orientation term isn't messing up the whole thing. So two ways to get larger flux. More density, more area, or both, okay? So in our case, we are going to not be counting fish, but be counting magnetic field. And our catcher is going to have an area A. And it's my suggestion to you that we define the flux as B times A. So that is the strength of the field times the area of the catcher. But we also have to remember that if you orient your area incorrectly, we have that the flux is 0. This is actually the maximum amount of flux you can have. This is the minimum flux you can have. And as you can probably guess, there's a middle ground, right? Just like in the fish example, we could tilt the ring so that maybe a few fish would swim through it, but not as many as they could, right? So let's come up with an orientation term, a way to talk about the orientation. What we're going to do is we're going to drop a normal, and I call this a normal line. So the normal line is used to discuss the orientation of the loop, or the catcher. I guess I will just say orientation of your area. Notice it is not a normal vector. A normal vector relied on a certain current direction, right? We wrap our fingers around the current direction, we get an arrow. Here there may not be any current, okay? But nonetheless, we can talk about a normal line. So here is my proposed formula. My proposed formula is going to be BA cosine of theta, where theta is the angle between the normal line and the magnetic field. So this is a angle between a line and a vector, not a vector and a vector. So this angle can only range from 0 up to a maximum of 90. Okay? If you have two vectors, then the arrowheads mean that they can point 180 degrees at most. But since one of them is a line, then it limits it to 0 to 90. So for example, if we look at this right here, what would be the angle between the magnetic field and the normal line there? 0, right? They're same along the same line. So cosine of 0 here is 1, so that indeed is maximum flux. You can see that that's how the magnetic field lines maximally pierce through the area, like fish swimming through the ring. Over here, the normal line looks like this. What's the angle between the normal line and magnetic field there? It'd be 90. So cosine of 90 is 0, hence no flux at all. And of course, it could be anything in between as well. I guess I can draw one of those. If the catcher looks like this, and the normal line looks like this, let me extend the magnetic field a little bit more. Looks like that. This angle is, doesn't matter which side you measure it, here or here, it's somewhere between 0 and 90, right? So that's my equation for the magnetic flux. It's the strength of the field times the area of the catcher times the cosine of the angle, such that there's some kind of way to orient the catcher in space. The only thing that I'm going to do is I'm going to add a n, because sometimes I don't want to just use one catcher, I want to use 10 catchers, right? It's like having a stack of rings for the fish to swim through. If you get a count every time the fish swims through a ring, a fish swims through, and ding, 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 it gets counted 10 times because it swims through the whole tube, right? So this actually allows me to get more flux just because I have more catchers. Okay? So this is just the number of loops. The number of loops have no units. Cosine also has no units. So the units of flux are just going to be the units of magnetic field and area multiplied by each other. Magnetic field is measured in Teslas, and area is going to be measured in square meters. That's always the units of flux. The units of flux will be the units of the field itself times the units of area. So for instance, if you're talking about, say, electric flux, anyone remember the units of electric field? There's two of them. So can you come up with one of them? What is it? Volts per meter, that's one of them. So the electric flux can be volts per meter times meters squared. That actually simplifies a little bit. What's the other unit for electric field?
Coulombs?
Not coulombs, it's charge. Think F equals QE. Newtons per, no. F equals QE. Newtons per coulomb. Newtons per coulomb times coulombs gives you newtons. All right. Well, so that would be the unit for electric flux. Another one would be newtons per coulomb times meters squared. Okay. So it's whatever the units of the field are times square meters, because you got the catcher there, the area of the catcher. This unit for magnetic flux, this comes up so often that you actually want an abbreviation for this. Tesla times meters squared is actually called a Weber. So if you ever see a Weber, that's what it is. So we now have an understanding of how to compute flux. Now we're ready to roll. Now, flux itself won't get you anywhere, but flux is a starting point. For instance, you may have remembered last time I was taking a magnet and pushing it in and out of a solenoid, right? Remember, you only had anything happening while there was motion. I think at one point I just set the magnet inside the solenoid to rest so I could talk about something, right? So if a magnet is sitting inside a solenoid, you can better believe there is a large magnetic flux to the solenoid. But you didn't see any current. The reason why is you can have a huge flux, but if it doesn't change with time, you get no electricity. So it's not just having flux. That magnetic flux has to change with time. That's where the EMF, that's where the induced current comes from. So if we take a look at the ingredients in flux, the ingredients are N, B, A, and theta. There are 4 different ingredients in flux. And at least one of them is going to have to evolve with time, and otherwise no EMF for you. Okay? So one of these must change with time. That will lead to EMF, potentially induced current, so on and so forth. Of course, even more than one of them could be changing with time, but we're just going to keep it simple. We're going to let each one take a turn. We're going to first change the magnetic field itself with time. Then we're going to change the area with time. This is going to be something called motional EMF. Then we're going to change the angle with time. This will lead us to what's called an electric generator. We generate electricity. We will even do something with the number of loops itself. We won't actually change it with time, but we'll do some kind of trickery. And this will lead us to something called an electric transformer. For instance, every time you plug in a power cube, you're plugging in a transformer surrounded by a piece of plastic, usually black, okay? For no particular reason that I can figure, okay? So once we have finished going over those 4 things, we'll have closed out Faraday's law, we'll have closed out homework number 7, and we will have closed out exam number 2, and we'll have closed out mostly magnetism. Although, as with all things in physics, you can't just put something down and expect it not to pop up its head later, right? So what I'm going to do with the time I have remaining, I'm going to do an example of 1. I'm going to see how far I can get with 2. And then hopefully I can get 3 and 4 done by Thursday so we can have exam number 2 material closed out this week. If not, no big deal. The homework 7, you guys have homework 6 due this weekend, right? So homework 7 won't be due till the following weekend. So if I need to bleed into next Tuesday a little bit, it won't be the end of the world. Okay, so let's do it.
Okay, I think this homework is tomorrow.
Oh, it is?
Yeah.
Okay, well then, I've already basically talked about everything before today, so I think we're good with that deadline, but I'll make homework 7 due sooner rather than later, just so that you don't have a gap in being able to do some work, should you choose to do so. Okay, so I'm going to do example number 1, which is going to be a magnetic field change with time. So here's my example. I'm going to have a magnetic field in a region like this. And this magnetic field is going to be uniform. And again, let me remind you what uniform means. It means uniform in space. So that means that any given spatial location doesn't have any stronger magnetic field than any other spatial location. However, it is going to increase with time. So the field remains uniform at any given time, but it gets stronger over time. So you can imagine that the field lines kind of are collectively bunching up over time. So into this region, I'm going to place something to catch some flux. What is it? It is a circular loop, just a piece of wire, a circular piece of wire. It has a radius of 1 meter. So the radius of your loop is 1 meter, and also let me give you that the magnetic field externally, I said it's increasing in time. Let me tell you by how much. By